Okay, so now what we are going to do is look at how do we design the other kind of extraction columns. We talked about spray columns where droplets are rising because of their buoyant force. But now let's do something about the agitated kind of systems. So so that will be like our mixer settler or rotating disc contactor. We'll just not do the design in a great amount of detail. We will try to look at just some of the common principles of design. Okay, so again, same problem we are going to do, uh, but before we do the actual problem, what we will need to do is we will need to estimate all these design parameters. Remember the design parameters that we are talking about? We are talking about hold up, drop size distribution, mass transfer coefficient, dispersion coefficient, pressure drop. Now instead of pressure drop, we will have motor power, agitator power that is required for all these for generating the drops, dispersing the drops of one phase into the other phase. So one of the things that we are going to start looking at is looking at mixer settlers and rotating disc contactors. So mixer settler, if you see, let me draw. Suppose there is a mixer and there is a settler here. Mixer and settler. So the aqueous phase comes in, organic phase comes in. They are going to mix. If it's a continuous mixer settler, this aqueous phase is coming in continuously, organic phase is coming in continuously, dispersion is generated. This dispersion sort of overflows into the settler and then it flows into this gap, and then the aqueous phase goes towards the bottom and aqueous phase is separated, and the organic phase goes towards the top, and the organic phase is taken out from the top. Now if you think about this mixer, because of agitation we can assume that we have well mixed behavior of both the phases. So if it is well mixed behavior, then the hold up is simply the ratio of the dispersed and continuous phase flow rate. So if I take this previous example, aqueous phase is coming in at, let's say, 10 meter cube per hour. Organic phase, let's say it is coming at 2.4 meter cube per hour. Remember, it is well mixed, so concentration everywhere, concentration in the sense concentration of the drops everywhere should be the same as the concentration of drops that are going out. And what is going out now? Aqueous is going out at 10, organic is going out at 2.4. So the hold up inside the vessel and hold up at going out of the vessel is simply 2.4 divided by 10 plus 2.4. Is that okay with everybody? Just think about it. Hold up is no longer in our hand. It is no longer decided by the slip between the two phases. It's no longer decided by the characteristic velocity. It is decided by the mixing behavior. If it is well mixed, then the concentration of drops, or hold up if you like, is the same at the outlet and at any point inside the column, inside the settler, mixer settler. Now when this organic phase comes in, now this is going to be broken up by the turbulence generated by this agitator, right? So the agitator is giving turbulence, and one of the mechanisms of breakage is that suppose there is a turbulent eddy. This turbulent eddy has some energy. So if I say u prime is the velocity of that eddy, rho multiplied by u prime square is like the kinetic energy of that eddy, or if you like, it is the kind of a pressure that is acting because of the inertia of that eddy when that eddy is in the vicinity of a drop. Okay, it's like a kinetic energy if you want. What resists the breakage of this drop is the surface tension force, and surface tension force we can characterize by sigma divided by d. It's not d prime, it is d. Okay, d is the drop size. So the equilibrium drop size I will get if I equate the two. If I equate the force because of turbulence and force resisting, so this is a breakage, it's like a driving force driving the breakage, and it is like resisting the breakage. When they are equal, then I will get a stable drop size. The drop will no longer break because now the surface tension force is resisting the breakage of that drop. Okay. This energy associated with turbulence, if you've done little bit of turbulence, you would know how to calculate this based on energy dissipation rate per unit mass. So if I say that I dissipate let's say 1 watt per kg or 5 watts per kg, then I can calculate this energy associated with the turbulence based on this assumption of isotropic and homogeneous turbulence. Let's not worry too much about turbulence just now, but it's like saying that the the intensity of turbulence is decided by how much energy we are putting in from this agitator. If I put in a lot more energy per unit mass, power per unit mass, so it is actually energy dissipation rate or power dissipation. So energy dissipation rate per unit mass or power dissipated per unit mass. The more power that I put in, the more turbulence that I am going to generate, and more energetic the eddies will be. U prime is the energy, or U prime square is the energy of the eddy. So now you can combine these two relationships, okay, do it for yourself, and you can get an estimate of how much the drop size would be. So people usually simplify this to, if I rearrange this expression, bring the d on one side and write everything else on the other side, and epsilon is power per unit mass. Remember, let me just clarify, epsilon is power per unit mass, it is in terms of watts per kg, whereas P by V is power per unit volume. So this is power dissipated per unit mass, whereas P by V is power dissipated per unit volume. Okay. So obviously, how are epsilon and P by V related? We can relate them, right? Based on density of the liquid, density of the continuous phase. That's how this density comes into picture. So this term is coming from here. It is coming from energy associated with turbulence. It is coming from breakage of drops. Breakage of drops due to turbulence and resistance due to surface tension. Couple of more corrections people have employed. One of the correction is to have a hold up raised to 0.5 term here. Now you see this, you see this dependence. The more power per unit volume that I put in, the lesser D32 it is going to be, right? Now if I have too many drops, then the drops will tend to coalesce with each other. So this term accounts for coalescence of the drops. So higher the hold up, higher would be the coalescence, and higher would be the Sauter mean diameter. and this mu d by mu c correction is there. It is actually the correction, that is surface tension is not the only force. Viscosity of the continuous phase and viscosity of the dispersed phase also dampens the part of the turbulent energy. So again, this is an uh, empirical correction term, but these terms have a meaning, and these exponents are sort of fitted, and the constant is fitted to match the experimental data. And so one such set of data you can take, one such values of constants you can take based on some literature. Let's assume that this is valid now. What I want you to do now is, for this case, so our epsilon d is 2.4 divided by 12.4. How much is this number? 2.4 divided by 12.4. This is 0.193. So something very similar to what we had in our spray column, 0.194 if you like. Okay. P by V now is 500 to 2000 watts per meter cube. So let's take some value, P by V equal to, let's say, 1000 watts per meter cube. Right? Remember, how would we relate the P by V and epsilon? P by V is power per unit volume. Let's put that. P by V is power per unit volume, watts per meter cube. Right? If I divide by density, right, divide this by kg per meter cube, then I will have watts per kg. So epsilon would be equal to P by V divided by rho of the continuous phase, in which the turbulence is there, in which agitation is creating turbulence. So take P by V equal to 1000 watt per meter cube. Take all the physical properties that we had taken last time and calculate D32. Okay, I'll give you a couple of minutes to calculate D32. With me, just let us write and calculate. So D32, if I wanted to calculate, it is 2.24. Sigma surface tension was 0.03 raised to 0.6. P by V, suppose I want 1000 watts per meter cube, then it is 1000 raised to 0.4. Rho C is now continuous phase is water, so 1000 raised to 0.2. Hold up, 0.194 raised to 0.5. And mu d by mu c. Mu d was, what was the mu d? Viscosity of the dispersed phase, organic, 0.005. Right? So mu d by mu c, 0.005 divided by 0.001. So that's 5 raised to 0.25. That's how we would get the D32. This would be in meters. This whole unit, if you take SI units, this whole bracketed term would have units of meters. Okay, and then interfacial area would be 6 times 0.194 divided by whatever this D32 we get. And you can see that the drop size is going to be much smaller as compared to what we had calculated for spray column. And therefore, when we had talked about these qualitative characteristics, mixer settler and spray column, suppose we are comparing mixer and spray column, what had we talked about? We had talked about mass transfer. We talked about high rate of mass transfer and low rate of mass transfer here, because the interfacial area is low, interfacial area is high level of turbulence, therefore high breakage of drops, therefore D32 is smaller, D32 is larger. You see how each characteristic in this table is related to the correlations that we are using. We can calculate each of these. That's what we are doing. We are quantifying each of these parameters. Of course, axial backmixing we are not considering just now. We are only considering mass transfer rate as a major parameter. because it depends on hold up, it depends on aim, it depends on D32 and so on and so forth, right? So you see how each of these terms are actually coming from the relationships that we are now using. And what you will find is if I take different values of power per unit volume, so you will, if you plot D32 versus P by V, you will find this kind of relationships. It is raised to power 0.4, negative side of course. As power per unit volume goes up, your D32 keeps on reducing. So we can take any value. We can take, suppose I have taken 1000 watts per meter cube here, and D32 we are getting is about 2 millimeter. If I take 5000 watts per meter cube, what would be our D32? It would reduce by a factor of 5 raised to 0.4, isn't it? It would reduce by 1.9 times, almost 2 times. It would become 0.001 approximately. It would be approximately 1 millimeter. So the interfacial area is going to become double. If I had 1000 watts per meter cube versus 5000 watts per meter cube, drop size is going to become almost half. Interfacial area is almost going to become double, right? Can you think of some drawback of this? Yes, one point is so much power consumption. Second point is if I make the drop size smaller, I require larger settler. We are talking about mixer and settler. You remember? Mixer is there, settler is there. When I wanted multiple theoretical stages, I am going to arrange mixers and settlers in series. Remember, suppose this is the one mixer we are doing calculations for. In this settler now, aqueous and organic phase has to separate, and then the heavy phase, aqueous phase will go out, and then the light phase will go to the next mixer. So we want a good separation in the settler. If I have 2 millimeter drop coming here, or as against that, if I have 1 millimeter drop coming here, the settler size required is going to be that much bigger if I have 1 millimeter drop. So the more power I put in the mixer, the better interfacial area I get, faster is the mass transfer, but I have to pay a penalty in terms of larger size of the settler. So it's an optimization exercise. How much power we are putting in, how easy the separation is, what is the mass transfer duty in terms of how much is the rate of extraction required. Okay, let's go forward. Okay. Next thing that we are going to look at is, of course, our continuous and dispersed phase mass transfer coefficient. So let's just take some correlation. Again, this is a correlation. This is like your Sherwood number now. This is an impeller Reynolds number. And this is a Schmidt number. Okay, so imagine that our mixer is 10 meter cube in volume. So approximately, let's say 3 meter diameter, or let's say 2.5 meter diameter. Let's make life simple. Let's say 3 meter diameter, and height would be, let's say, 1.5 meters. So liquid volume does not matter just now. Well, okay, liquid volume, we can keep 10 meter cube as a liquid volume. Okay, so if it is 3 meter diameter, cylindrical, then the height of that cylinder would be about 1.4 meters. Now suppose we want power per unit volume equal to 1000 watts per meter cube. That means power that I want to put in would be 10,000 watts. Now who's going to supply this power? Agitation is going to supply this power, isn't it? Where did our picture go? Our picture is way back. Is it? Picture is way back. Okay, this motor is giving the power, right? Agitator is dissipating that much amount of power into the liquid. So we can all relate it to the diameter of the impeller, and yeah, so this power has to come from impeller power number rho n cube and d raised to 5. So I'm saying the mixer is like this. Agitator is there. D is the diameter of the agitator. T is the diameter of the tank. Okay, this diameter of the tank is 3 meters. Liquid height doesn't matter much just now, it is 1.4 meter. Okay, diameter, let's assume it is some kind of a let's say it is like a Rushton turbine. Have you heard of different kinds of impellers? Or a pitch blade turbine? We talked about it last time in our CRE course. So pitch blade turbine, so let's say NP is about 2 and diameter is tank diameter divided by 3, so it is 1 meter. Okay, so now calculate what would be the speed with which I would want to rotate this agitator so that I would be able to dissipate 10,000 watts. Speed of agitation. And once you calculate the speed of agitation, you can put it into this Reynolds number and you can use these properties and the tank size and you can calculate the value of Kc. Okay, I'll give you a couple of minutes to do this. Okay, so just let us just calculate so that everybody is aware what we are doing. So we want to dissipate 1000 watts per meter cube. 10 meter cube is the liquid volume. So the total power I want to dissipate, total power I want to deliver to the liquid is 10,000 watts. So this is going to come from the impeller agitation. So this 10,000 is equal to NP. We said power number is 2, rho is 1000. It is continuous phase is water, aqueous phase 1000, N cube, and 1 meter diameter impeller raised to power 5. So N cube is going to be equal to this. So N is going to be about 1.7 revolutions per second. Revolutions per second is about 100 RPM, 100 revolutions per minute approximately. Okay. Now if I want to calculate the Kc, now let's do it here. Impeller Reynolds number, if you want to calculate N, so that is 1.7 d square, diameter is 1 square, rho c 1000, mu c 0.001, this whole thing raised to 0.83. Schmidt number of the continuous phase, Schmidt number of the continuous phase is water, mu 0.001, diffusivity, okay, what was the value of diffusivity? I don't remember. Yeah, 1 into 10 raised to minus 9 in the continuous phase. 1 into 10 raised to power minus 9, mu divided by diffusivity, and rho 1000 raised to 0.5. 0.052, that's the constant that has come. All these constants and powers are coming from somebody's experiments. They have done experiments, they have measured and they have correlated it to fit these constants to the data. Kc, tank diameter, is 3 meters. Diffusivity is 1 into 10 raised to minus 9. And that's how you will get a value of Kc. Just check your calculations. Okay, so that's how you will get Kc, and you will find that the interfacial area is so large, therefore I get much higher rate of mass transfer in a mixer settler. Okay, shall we go forward? If there is a doubt, we can always pause and think and revisit any of these videos. So let's go on now. Let's go on to the next thing that is there. So the next thing that is there is rotating disc contactor. Now this kind of contactor is sort of somewhat an intermediate between a mixer settler and a spray column. So imagine what we talked about in this rotating disc contactor. There is a shell. This is your shell outside. These are the discs that are rotating. These are the stationary stators that are there outside. Remember we talked about this picture last time. Right? You remember this? Either these could be discs or these could be impellers. Now we are taking them to be discs right now. Now the way this equipment behaves is somewhat an intermediate of a spray column and a mixer settler. So that's why it is so very popular. So there are some standard um, geometries that people have recommended, that the opening, so these are like, so if you visualize the top view of this, so this would be, or maybe an isometric view, this would be the shell, outside shell. Diameter of that outside shell is T. There is a shaft that goes in, there is a disc, and there is a empty space, and this is the stator. The stator ring is like this. This is your stator ring, and this black thing is your rotating disc. So now you imagine that a bunch of discs, stator rings, and bunch of stators, rotating disc and stationary stator. So it is like a the stationary stator is like a donut, right? It is like a washer. If you have seen washers, right, that go between the bolts and to support the head of that bolt. So it would be like this. You've seen washers. Looks like a donut or a washer, and then disc would be here. This disc would be rotating. It is connected to this rotating shaft. The dispersed phase that we are supplying is, let's say, supplied through this distributor. The droplets are generated. So each of these compartments behaves like a mixer where power is put in by the rotation of the disc. So that creates the breakage of drops here. It causes the mixing of the drops, breakage as well as mixing. Mass transfer occurs here. The drops are going to the next stage through this gap. Are you able to visualize? Drops are coming from bottom to the top through the gap in this washer or donut, if you like. Then it comes into contact with this disc again. Again here it gets mixed up. Again it gets broken up further. Mass transfer occurs. The drops go to the next stage through this gap. Again mixing happens. Again it goes to the next step. Again mixing happens. Again it goes to the next, and so on. So the organic phase, let's say, is put in continuously. This phenomena of droplets coming, getting mixed, goes from subsequent stage to stage, and then goes out from the top. Aqueous phase that we put in goes to the first topmost stage. It flows through this gap. So now you see this gap has to do two things. One thing that this gap has to do, these stators have to do, or these donuts have to do, is that they have to prevent axial mixing. That's how they are blocking. They are blocking part of the flow. They are physically blocking part of the flow. And in whatever opening that exists in that washer, in that donut, if you like, if you look at the top view of the donut, the droplets are coming upwards in this gap, and the aqueous phase is going downwards. You see, so the droplets come up and aqueous phase comes down through this gap, right? So it does provide a counter current contact, and the extra agitation that is provided by these rotating discs creates the breakage of drops. So we are no longer dependent on the large drops that are generated by the distributor. We can break them down into smaller drops so that we can get good mass transfer, good interfacial area. I hope you people are able to visualize. If not, pause and watch a video, or pause and think, and maybe read some research paper. Okay, so people did experiments, and people gave some kind of recommended geometry that the size of the opening of the stator should be about 2/3 of the size of the tank. The gap between the spacers should be related to tank diameter raised to 0.68 and so on. And D, impeller diameter or disc diameter, should be about half of the tank diameter, because we want a little little higher diameter, because there is no agitation. The breakage is happening because of the disc rotation, because of the shear generated by this rotating disc. Now if you see the characteristic velocity, so this kind of design procedure for this kind of equipment is going to be partly like a spray column, because there is partly a continuous flow of drops upwards, but there is also breakage because of agitator, breakage and coalescence, because of agitator. So if you think about this characteristic velocity u0 that we talked about in spray column, here characteristic velocity we talked about in spray column, if your agitation speed is low, the energy dissipated by these discs is so small, the amount of breakage of the drops that will happen will be very, very small. So essentially the characteristic velocity would be like the spray column. It would be decided by the distributor, the physical properties, and so on, like the spray column, like here. Do you agree? Whereas if your speed of agitation is high, then I would have so much breakage that essentially it does not matter what size of drop is generated by the distributor. It is all governed by the breakage that is caused by the disc rotation. And then the breakage due to disc rotation can be characterized by this kind of relationship, depending on how much power we are putting in through the rotating discs. So people tried to classify these two effects. People said that under low agitation speed it behaves like a spray column, but at high agitation speed it behaves like a mixer. But the only advantage is that I have a series of mixers, one on top of the other. But because these openings are large, there is heavy axial mixing between the two compartments. So we need to account for axial mixing if we are talking about rotating disc contactor. The gap between the stator, the opening of that stator ring is so large, it has to accommodate the axial, the flow of droplets upwards and the flow of continuous phase downwards. That's why that opening is large. I have to be able to take out the discs from the top of the column. So the opening has to be larger than the size of the rotating discs. So you have to account for axial mixing, but that's little later. What I want to talk just now is only these two regimes. At low speeds, something like a spray column, some behavior like a spray column would happen, and at high rotation speed, something like a mixer kind of a hydrodynamic behavior would happen. So first of all, what people did is did experiments and correlated this critical speed. They measured the value of the critical speed and they correlated it to the properties. So what I'm going to give you is the empirical correlations for critical speed. So these are all empirical correlations. People have come out with these empirical correlations based on large number of experiments, and these powers and exponents are constants are fitted to the experimental data. So first of all, the critical speed is given by this relationship. Okay. Then the characteristic velocity is related to the geometry of the rotating disc contactor. It is also related to the power that is put in through the rotation of the agitation. So you can see in region 1, where it behaves like a spray column, this power of n is very small. So it is as if there is practically no effect of agitation. Entire characteristic is decided by this value. We had seen this number sigma delta rho g by rho c square. It is the same number that we had seen when we had talked about spray columns. Sigma delta rho g by rho c square. And of course other geometry parameters are there. But when you go to region 2, essentially it is controlled by the agitation. Then you see that power of n is high. Right? So then you see that significant breakage would occur because of the disk rotation, and then u0 would be fairly small. So what I want you to do is consider a 0.5 meter RDC. That means now T is 0.5 meter. Let's say it is 10 meter long. Assume that power number for each disk is 0.1. What I want you to calculate is NCR, the critical speed, from this equation 1. I want you to calculate power per unit volume at NCR. How much power per unit volume is dissipated at NCR? If I want to take the actual speed as, let's say, 1.2 times the critical speed, so that means we will calculate critical speed first, then we will say, oh okay, I will want an operating speed something like this, say 1.2 times NCR. Then I want you to calculate using this n, using this u0. I want you to calculate u0, and then once you know u0, then you can calculate your epsilon d using our ud by epsilon d slip velocity uc by 1 minus epsilon d is equal to u0 1 minus epsilon d raised to power 1. Okay, and then I want you to calculate, of course, d32 we are going to calculate like this now, because now we are at a speed more than the critical speed. Okay, so and then I want you to calculate the interfacial area. So I'll give you 5 minutes to calculate. Shall we continue further? It's just a matter of substitution. Would you be able to calculate? Just take one example. So let's just calculate the critical speed. So G 9.81, R radius. Now we have a 0.5 meter RDC. So 0.5 meter is our value of T. So then diameter of the disc is half of that, 0.25. So then the radius of the disc would be 0.125 meters. Okay, so let's just take 0.125 critical speed square sigma 0.03 cube rho c 1000 mu c 0.001 raised to power 4 into 9.81. This whole thing raised to 1 by 4. Delta rho 900 and 1000. So delta rho is 100. Rho c is 1000 raised to 3 by 5 is equal to 180. Right? So then we can calculate NCR. Okay. Now U0, if I want to calculate, uh, um, before that I would like to calculate this. So NCR we have calculated. Power per unit volume at NCR. How will we calculate that? See, our rotating disc contactor is 10 meters long. Right? So this is 10 meters long. If I say that the gap between the compartments Z, that's the gap between these two compartments, is 0.62 times T raised to 0.68. T is what? T was 0.5 meters. So this Z would be equal to 0.62 into 0.5 raised to power 0.68. So this would be 0.62 multiplied by 0.5 raised to 0.68. This Z would be 0.38 or 0.39, or just say 0.4 approximately. Approximately 0.4. Okay, so just doing the calculation little fast. Okay. So in 10 meters, how many such compartments would there be? In 10 meters, if the gap between the compartments is 0.4 meters, in 10 meters, there would be 25 compartments created by these washers or by these donuts. And there would be 25 discs. Okay. So now when we are going to calculate power per unit volume at NCR, so speed we have calculated, NCR we have calculated, power per unit volume would be total power divided by total volume. Total power would be number of discs multiplied by power put in by one disc, isn't it? And total volume. So number of discs, there are 25 such compartments. That means 25 such discs. So 25 multiplied by power put in by one disc, NP rho n cube d raised to 5. Right? And now this n is, we are calculating at NCR. So this is NCR. Volume 0.5 meter diameter and 10 meter long. So pi by 4 multiplied by 0.5 square into 10. That will be the total volume. So that's how you would calculate power per unit volume. And now if our speed is actually 1.2 times the NCR, then whatever NCR we calculate from here, We are going to take 1.2 times that. Now the actual power per unit volume will be same, this whole thing, same number. Only thing is, instead of this NCR, it will be N. So it will be 25 into NP into rho into N, 1.2 times the NCR, t raised to 5 divided by pi by 4, 0.5 square into 10. That will be the total power per unit volume in terms of watts per meter cube. Okay. And then you can calculate the drop size from this kind of relationship. All you need is your power per unit volume, because surface tension you would know, rho c you know, power per unit volume at 1.2 times NCR we have calculated. Hold up, UD, UC. To get to the hold up, what do we know? To get to the hold up, how will you get hold up now? Hold up is going to come from this U0. So we'll have to calculate U0, right, at 1.2 times NCR. At this value of N, we have to calculate the hold up, isn't it? So what do you know here? G you know, R you know, speed you know, 1.2 times the minimum. All these properties you know, delta rho, rho c you know, these geometry parameters you know, okay, this properties you know. So then U0 can be calculated. So calculate U0 at N equal to 1.2 times NCR. Okay. Now our slip velocity relationship, correct? Diameter is 0.5 meters. Now you can take organic and aqueous flow rates, same, say 10 meter cube per hour is the aqueous flow rate, and whatever whatever value was there, 2.4 meter cube per hour of organic flow rate was there, right? So our aqueous was 10 meter cube per hour and our organic was 2.4 meter cube per hour. Isn't it? So then, and the diameter is known, so UC you can calculate, UD you can calculate, U0 you have estimated, so calculate epsilon D. Okay. Once you calculate epsilon D, mean drop size you have calculated, and interfacial area you can calculate now. Okay, so this is how you would do the calculations. Okay, so I'm just doing it little quickly, but you actually actually do the calculations and make sure that you get a value for each and every number uh, that is to be calculated. Only once you get an actual number, you will be able to sort of understand the meaning and so on. And I would recommend that you put it in an Excel sheet so that you can keep on playing with the geometry parameters. You can play with, suppose what will happen if I have 1.1 times NCR, what if I have 0.8 times NCR, it behaves more like a spray column. What if I put in too much power, 2 times the NCR, what kind of drop sizes do I get, what kind of interfacial area do I get. Then we can go on forward. We can use mass transfer coefficients to estimate using some kind of relationship. Again, this relationship is there, we saw that when we talked about spray columns. So Kc and Kd you can calculate. Now you will, the slip velocity you know, epsilon you know, slip velocity you know, all the physical properties you know, diameter you know, so Reynolds number you know, and then you can calculate Kc and Kd, and then think about how you would use this to calculate the outlet concentration. So what we are doing now is we are taking this 10 meter cube per hour flow rate of aqueous in a 10 meter tall RDC. Inlet is 5000 ppm, outlet is what we want to know, 2.4 meter cube per hour we have put in. In the spray column, what we had done, I had told you that outlet we want 50 ppm, I had asked you to calculate the height in the spray column problem. Now I am giving you the height. I want you to calculate the outlet. But again, if I neglect the axial mixing, again, if I make the assumption that it is plug flow, so what we will do is, this is our RDC. This is our RDC. 10 meter cube per hour of aqueous is coming in. 2.4 meter cube per hour of organic is coming in. This aqueous entry is 5000. This is 0. Now again, if I take a differential balance, the mass transfer coefficients I know and the height I know is 10 meters. I can calculate what would be the outlet concentration, right? So we are doing the same balance over a differential element dz, but in the spray column problem, this spray column problem, I had told you that we want 99% extraction, and I wanted you to calculate the height of spray column. Now I'm giving you the height and I'm asking you to calculate what would be the outlet concentration. So same kind of differential balance you will be able to use. Only thing is, it just depends what is to be calculated now, right? So try doing this problem. Okay, do all these calculations yourself, put them in Excel. So it would be that whole template will be with you. Anytime you want to do an extraction problem, you can just pull up that Excel sheet and put in the numbers and you get a answer. And also, if you put it in Excel sheet, you can always play around what happens to the critical value. If I take 1.2 times the critical speed, 2 times, 3 times, 0.5 times, see what happens, how much the outlet concentration in the aqueous phase changes depending on the value. Also, I would like you to compare the values of mass transfer coefficient, interfacial area, uh, the hold up for spray column, for mixer settler, for RDC, and see how these parameters behave. Spray column will have a very low interfacial area. Mixer settler will have a very high interfacial area. RDC would be somewhere in between. So I want you to actually calculate for yourself and see for yourself all these numbers. Only then you can be be confident. And one more thing is, don't mug up any of these relationships. If they are required, they will be given in the exam.